Let us look at proposition number 18 of book 13 of Euclid's Elements. The proposition says to set out the sides of the five figures and compare them to one another. Set out the diameter AB of the given sphere. Cut it at C such that AC is equal to BC. So basically we are taking the midpoint of AB. Cut AB at D such that AD is equal to 2 times BD. So here AD is 2 times BD. Draw a semicircle AB. Draw CE perpendicular to AB and DF perpendicular to AB. Draw AE, AF, FB and EB. Now, since AD is equal to 2 times BD, AB is 3 times BD. So, in conversion, AB will be 1.5 times AD. Triangle AFB is equiangular with triangle AFD. So, which means AB is to AD is equal to AB square is to AF square. Now, since AB is to AD has this relationship, that is AB is 1.5 times AD, that means AB square is also 1.5 times AF square. We have seen previously that the diameter of the sphere square is equal to 1.5 times the side of the pyramid square. So that means AF is side of the pyramid. AB is to BD as AB square is equal to BF square. Again, because the triangles are equiangular. So AB square is equal to 3 times BF square because AB is 3 times BD. Again, we know that diameter of the sphere square is equal to 3 times side of the cube square. So that means BF is the side of the cube. AC is equal to BC. Therefore, AB is equal to 2 times BC. AB is to BC is equal to AB square is to BE square. Again, because of the appropriate triangles being similar. So that means AB square is also 2 times BE square. And again, we know that the diameter of the sphere square is equal to 2 times side of the octahedron square. So therefore, BE is the side of the octahedron. Draw AG perpendicular to AB such that AG is equal to AB. Draw GC. So join G and C, which means it is going to intersect this semicircle. So that intersection, let's name it as H. Draw HK perpendicular to AB from H. So GA is equal to 2 times AC. Since AG is equal to AB. So now AG is to AC. AG is to AC as HK is to KC, because these two triangles are equiangular. And since AG is 2 times AC, that means HK is also 2 times KC. So now let's square both the sides. So we get the square on HK is equal to 4 times the square on KC, and HK square plus KC square is equal to 5 times KC square. So here we have added KC square to both the sides. Now what is HK square and KC square? HK square, KC square, this is a right angle triangle. So which means that HC square is equal to HK square plus KC square. So we can say HC square is equal to 5 times KC square. Now, HC is equal to BC, which implies BC square is equal to 5 times KC square. Now, AB is equal to 2 times BC and AD is equal to 2 times BB. BD is equal to 2 times CD. So, BC is equal to 3 times CD. Again, squaring both the sides, we get BC square is equal to 9 times CD square. So, here we have BC square is equal to 5 times KC square and BC square is equal to 9 times CD square. That means what? That means KC square is greater than CD square, because the square on KC is 1/5 of the square on BC, whereas here CD square is 1/9 of BC square. So KC square is greater than CD square, which implies KC is greater than CD. Let CL be equal to KC. So let's mark that. CL is equal to KC. And we draw a perpendicular from L to intersect with the semicircle. BC square is equal to 5 times KC square and AB is equal to 2 times BC and KL is equal to 2 times KC. So which means AB square is equal to 5 times KL square. But we know that the diameter of the sphere square is equal to 5 times the radius of the circle from which icosahedron was described, square. So KL is the radius of the circle from which the icosahedron has been described. So KL is a side of the hexagon, because the radius of the circle is equal to the side of the hexagon. Diameter of the sphere is made up of the side of the hexagon and two sides of the decagon inscribed in the same circle. So here, hexagon, we have side of the hexagon is KL, and it is also made up of two sides of the decagon inscribed in the same circle, and both these two are equal. So here also we have AK is equal to BL. So KL is equal to side of the hexagon, AK is equal to BL, which means that AK and BL are sides of the decagon. BL belongs to a decagon and BL belongs to the decagon and ML belongs to the hexagon. So HK and KL are equal to each other because they are both 2 times KC. Yes. So here if you notice, HK is 2 times KC and KL is equal to 2 times KC. So that means MB, so let's join them. MB belongs to a pentagon. So in a right angle triangle, if one of the sides, non-hypotenuse side, is a decagon and the other side is a hexagon, then the hypotenuse is up, it belongs to a pentagon. So that means MB belongs to a icosahedron. Now, BF is the side of the cube. BF is the side of the cube. We cut BF in extreme and mean ratio at N. So let's cut it in extreme and mean ratio at N. Let NB be the greater segment. Then NB is the side of the dodecahedron. Now AB square is equal to 1.5 times the AF square. AB square is equal to 2 times BE square. AB square is equal to 3 times FB square. So if AB square contains 6 parts, AF square contains 4 parts. DE square contains 3 parts. FB square contains 2 parts. AF square is equal to 4 by 3 of BE square. 4/3 of BE square. And AF square also has 2 times FB square. AF square is 4 parts. FB square is 2 parts. That means 2 times FB square is equal to AF square. B square is equal to 1.5 times the FB square. So that means pyramid, octahedron, cube are in rational ratios. So what we do is look at it like this. AF square is to FB square is equal to 1:2, which is rational. Similarly, AF square is to B square is equal to 1:4/3. So which is again a rational ratio. So like that, we can say pyramid, octahedron, cube are in rational ratios. Or rather, the sides of the pyramid, octahedron, and cube are in rational ratios. Now, MB is the side of an icosahedron and NB is the side of a dodecahedron. They are both irrational, that is minor and epitome. MB is minor and NB is epitome. So they don't form any rational ratios with each other and with any of the others. So now let's understand the relation between these two, which is greater. So triangle FBB is equiangular with triangle FAB. So that means the sides about the equal angles are in proportion. So that means BB is to BF as BF is to AB. And because they are equiangular, BB is to AB is equal to DB square is to FB square. Or inversely, we can say AB is to DB is equal to FB square is to DB square. And we know that AB is 3 times DB. That means FB square is also 3 times DB square. AD square is equal to 4 times DB square, since AD is equal to 2 times DB. Yes. So, which means AD square is greater than FB square, which implies AD is greater than FB. AD is greater than FB, which means AL is going to be much greater than FB. So when we cut AL in extreme and mean ratio at K, remember KL is hexagon, side of the hexagon. KA is the side of the decagon. So when we cut AL into extreme and mean ratio at K, KL is greater than KA, because KL is side of the hexagon and KA is the side of the decagon. When FB is cut in extreme and mean ratio at N, NB, which is the side of the dodecahedron, is greater. So that means KL is greater than NB. And since KL is equal to LM, we can say LM is greater than NB, which means MB is much greater than NB. So which means side of the icosahedron, that is MB, is greater than side of the dodecahedron, that is NB. So that is the kind of relationships that exist between the sides of the various figures, that is, or solids, that is pyramid, cube, octahedron, icosahedron, dodecahedron. That was proposition number 18 of book 13 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.